In this video, we are going to finish up our discussion on section 4.4, percents and compounding. In particular, this video addresses the last two of our objectives for the lesson, calculating the multiplicative average, and we'll also look at money and compound interest. Some basic background information, thinking just in terms of money. Well, if you are going to invest money in something, generally speaking, you expect a return on the investment. If I give you $100 to start a Girl Scout cookie business, in general, there is risk that your business could fail, and so I want more than $100 back. I want a return on my investment because I'm taking a risk that I get nothing and I lose. So when I invest, there's usually the return is usually expressed as some kind of a percent. For instance, when you put money in a checking account or a saving account, they can tell you, we will give you 2% per year. When you borrow money from a credit card, they might tell you, we will charge you 12% per year, or whatever, depending on your credit scores. In our first example that we'll consider, let's say I invest $100 at 10% return for 1 year. How much money do I get back? Of course, I get my original $100 plus that 10%, giving me a total of what Alex told me, 110%, or $110. Well, if you're looking at a percent for 1 year, it's fairly straightforward. What about for 5 years, though? How much do I get back for investing over years? Sometimes students will simply say, well, 10% at 5 years is 50%. And so they would say $50 interest, I'd get back $150. That type of interest is called simple interest, where the only time interest gets charged is on the original amount. Nobody in the financial world uses simple interest. That might be the kind of thing that you would give to friends or relatives, or, you know, with friends and relatives, most of the time it's like, all right, well, there's no interest at all because you're helping somebody out. Banks, credit cards, nobody does it that way. Everybody in the financial world uses compound interest, where they look at it and say, well, I put in that $100, and after 1 year, I got $110. In year number 2, they're going to charge you interest not based on the original 100, but on the $110 that we already had. So you're getting interest on top of the interest that you already earned. And in this instance, after 2 years, interest on top of interest gets you to $121. Oh, another extra dollar. You go to year 3, you'll get interest on the $21, and then you will get interest on that, and on that, and on that. The interest compounds and stacks on top of itself. Consider this then. Recognizing that we didn't finish the last problem because it was just designed to introduce the idea. Suppose in 2010, an 1801 half dollar was in excellent condition and it was worth $35,000. Now, in 1801, you put 50 cents into getting this coin, and now it's worth 35 grand. Is that a great investment to go from 50 cents to $35,000? Well, consider this then. If we were to put that same 50 cents in, invested at 4% per year, what is that investment worth now? Keep in mind that we're looking at this and saying the original value was 50 cents. In 1 year, it went up 4%, an increase of 4%. In 2 years, it went up another 4%. For 3 years, another 4%. 4 years, another 4%. Well, how many times are we going to have to include this 4% increase? Yeah, how many times how many years have gone by from 1801 to 2016? So, since there are 215 years have gone by, we need to write down 1.04 215 times. Fortunately, we have a smarter way of writing it out. How do you write out repeated multiplication? Yeah, we'll just take the exponent, 1.04, and we need 215 of them. Well, if you've got your calculator handy, let's stick this thing in and see what we get. How much would it be worth with 215 years of interest attached to it? 0.5 times 1.04 to the 215 power. And so there we go. 2296.88. So 2296.88, rounding it to the nearest. So what do you think? Overall, they make a smart investment? Well, they made a smart investment based on 4% interest. If we had a different interest rate over a period of 215 years, who knows what it would have been. But based in this situation, buying this coin was way better than putting it in some bank account that draws 4% interest for 200 years. I'd like to ask, what would have been different if it were an 8% interest? How would the problem change? Well, in that instance, we would have had a 1.08, and in that instance, at an 8% interest, it's worth a little bit more. You know, only $7.7 million. That's not that much. Pretty amazing how big of a difference just 4% interest makes. All right, suppose an investment yields 12% compounded monthly. How much does it grow in 1 year? How much does it grow in 3 years? One of the problems that this particular problem is giving us are mismatched times. The interest is compounded monthly, but we want to know how much it's worth in 1 year. Year and time. Now, in order to progress with this, we need to make certain that the time matches. In order to fix this, let's just do a quick conversion. Let's convert 1 year into months. Okay, so if we have 12 months, then this is telling us we'll start with the original amount of the investment, and if we're compounding it 12 times over 12 months, how much is the interest for each month? It's not 12% each month. 12% compounded monthly means for the entire year you have 12%. And then it's going to be split up amongst those 12 months, so this is another way of writing it's 1% interest per month. So we would wind up with 1.01 compounded 12 times. Entering that into the calculator, we get 1.1268, which is 68, which is equivalent to 12.8%. In finance, this is called the annual percentage yield. It's also called the effective rate. Because interest gets charged on top of interest, because the interest is stacking and compounding, you actually wind up with an interest rate that is different than what is reported. Well, what would be different then if we did this over a period of 3 years? Well, in 3 years, 3 years is 36 months. So we wind up with something very similar. We'd take that 1% per month and compound it 36 times, giving you overall a 43% return on your investment. Well, working through problems like this can be made more simple with the compound interest formula. You are expected, one of the expectations for this particular class is that you've already taken Algebra 2, so you would have worked with the formula, and so this is a bit of a review over earlier information, not so much a brand new introduction. The compound interest formula, though, the amount the money grows is based on the principal multiplied by 1 plus the interest rate change. 1 represents the original 100% of your investment. The interest rate for the year is split up amongst the number of times or the number of compoundings that you have each year. And then you'll have the number of compounds multiplied by the number of years. Oh, I had the variable backward. Well, it's just a dummy variable, but n is the number of compounds per year. I had written k previously. We'll just make those match. All right, let's consider this. What is the effective rate, your annual percentage yield? That's what we just did. If you have a 16% interest rate compounded daily, which, by the way, credit card companies love to charge interest daily. Well, in this instance, we can go through and use our formula. And let's start putting in what we know. What is the amount of your original investment? We'll look at it and say $1 for 100%. What is the R value? 0.16. We'll take that percent and represent it in its decimal format. How many compounds are there for the N value? How many days are in a year? And then we'll have 360 compounds for a period of 1 year. And we now have something that we can put into our calculator. Right, so we have 1 plus 0.16 divided by 365 to the 365 power. And we wind up with 1.1734. So 1.1734 is 1% increase. We know we have to subtract off the original amount to get the increase. So 0.1734, which is a 17.34% interest. Indicating that if you were to have money on a credit card and they tell you you have a 16% interest, if if you don't pay off that money, you will actually be charged 17.34% interest over the year. Okay, continue this one. This is our first example where we will examine the multiplicative average. Suppose growths for an investment for the last 4 years were 10%, 28%, 32%, and 7%. What is the cumulative growth over those 4 years? Straightforward. We'd have a 10% increase, followed by a 28% increase, followed by a 32% increase, followed by a 7% increase. Grab your calculator, multiply them out. What do you get? Yes, one more. All right, so Dylan went through, crunched the numbers for us, and gave us 1.9886. We know we have to subtract off the original amount, giving us 0.9886. Overall, meaning we have a 98.86% return on our investment. So we've almost doubled our money in 4 years. That's a pretty good investment. What is the average growth per year? This is a part where it's almost universal. Students will make a mistake here. Because the overwhelming majority of students think, well, if we're going to take an average, we'll just take this piece and divide it out by 4. And we'll say 98.86 divided by 4 gives us 24.715. Many students will say, this is your interest rate. Well, let's go through and say, let's take this interest rate and compound it 4 times. What do you get? After putting it into our calculators, we get something that is 2.4184, and that's not the 1.9886 that we wanted. So what went wrong? Everybody knows that you just divide by how many there are to get the average, right? That itself is the problem. Up until this point, most students have only ever worked with the arithmetic average. When you do the arithmetic average, you add up the different values and divide by how many there are. Well, when we are doing our calculations, were we adding numbers? No. So it doesn't make sense to do an arithmetic average. Instead, you need to do the geometric average. And in that instance, we're looking for what is the interest rate that would get used 4 times. In this instance, we're looking at 1 plus the interest rate, compounded 4 times, will give us this 1.9886. Using the geometric average, we will be able to figure out the average percentage rate. So how do we solve this now? How do you get rid of an exponent? Well, a power raised to a power, we know that we would use the reciprocal of 4 is 1/4, which is just another way of writing the 4th root. And we will take the 4th root, then giving us 1 plus r equals, and we'll have to go to our calculator for this one, 1.9886 to the 1/4 power tells us 1.1875. Come on. 1.1875. We'll subtract the amount for the 1, and we get our interest rate of 0.1875, which of course we know is an 18.75% interest rate. And frankly, if you could have an investment give you a return of almost 19% per year on average, that is fantastic. That is so good that you should almost question whether they're doing something illegal, like what happened with the Mets a few years ago. In our last example, same type of thing. Find the cumulative growth and the average growth. So what were the growths? Up 10%. How do you write out up 10%? That's 1.1. Then you have down 8%. How do you write losing 8%? If you've lost 8%, how much have you kept? You're keeping 92%, so we'll take 0.92. Up 13%, that's 1.13. Up 35%, that's a great year, 1.35. And down 20%, 20% off of 100% is 80. So that means you're keeping 0.80. Multiply this out, and we can figure out the cumulative growth. It's 1.1 times 0.92 times 1.13 times 1.35 times 0.8. And the overall effect, 1.235, which is giving us a 23.5% overall return on our investment. Well, at least we didn't lose money, but it could be better. The average growth then, well, how many years is this over? That included 5 years. So we would have 1 plus the average rate to the 5th power will give us this 1.235. In order to solve it, we will have to take this then to the 1/5 power. And so going back to my calculator, take that to the 1/5 exponent, giving me 1.0431. So 1 plus r is equal to 1.0431. Thus, r is 0.0431, which is a 4.31% average rate. So you're earning 4.3%. Hopefully that's staying above the rate of inflation, so at least you don't lose buying power. And this finishes off our discussion into section 4.4, percents and compounding. A lot of information here. We spread it out over an entire week, mostly because percents really, really are important. They play a huge role in finances, and let's face it, you're not going to get through life without having to work with finances.